In this video, we explore the photoelectric effect and its consequences on the modern physics revolution. In order to start our analysis, let's think in the following experiment. Suppose that you have an electroscope, and by using a glass bar, you charge it with negative charge. As usual, the electrostatic force bends a gold foil up, due to repulsion. Then, you approach an ultraviolet lamp, and you can see that the gold foil returns to the original position, meaning that the electroscope has discharged. Let's think of what is the reason for the electroscope to discharge. This means that there is a leak of electric charge, but the device is completely isolated. If we use classical physics, we are in a big trouble, as there is no way for an electromagnetic wave to discharge an electroscope. Then, in 1905, Albert Einstein published a paper explaining the phenomenon. He used a fairly new idea, developed 5 years before by Max Planck. Einstein assumed that the light was composed of particles instead of waves. He called the particles light quanta. With this model, it is easy to understand the process. If we make a microscopic image, we can see that the charge, distributed on the surface of the metallic plate of the electroscope, is composed of tiny particles called electrons. Actually, electrons were discovered less than a decade before Einstein's proposal, by Joseph Thomson. Then, a quantum of light, with enough energy, can kick out one electron of the surface of the material. If we think of the huge number of light quanta that flood the metallic plate, then we can understand how the electroscope discharged. Later studies used a more controlled device. It consisted of a vacuum tube, where two electrodes that have a potential difference, V, between them. The illuminated electrode was the anode, and is also called the photoelectrode. If the current was measured, it was zero when there was no light. As soon as the light source was turned on, a current appeared. The electrons emitted from the anode are called photoelectrons and collected at the cathode. Interestingly, only when the light used was in the ultraviolet range, the effect was present. This means that using red, orange, yellow, green, or blue light, there was no current measured. Also, the intensity of the light was not important, only the frequency. Then, we can describe the characteristics of the photoelectric effect as follows. The current appears immediately when the anode is illuminated. There is a minimum frequency for the effect to exist, and depends on the material used on the anode. The intensity of the light is not important up to a certain point. There exists a negative potential where the current is zero. Now, let's turn our attention to the theoretical model developed by Einstein. We know from the classical physics that the work spent to move a charged particle through a potential difference is the product of the electric charge times the potential difference. In this sense, if the electric charge is an electron with charge minus E, then we have, using the work-energy theorem, we can see that the maximum kinetic energy, that a photoelectron at the surface of the anode, is simply written as follows. Two important points to notice are the following. The photocurrent is zero at minus delta V, because at such potential difference, the electrons are forced to remain at the anode. This is an expected result due to the electrostatic force generated by the cathode. Also, we can see that the photocurrent grows as function of the potential difference, and reaches a saturation point. Moreover, the intensity of the light source is not included in the equation, then it does not matter. On the other hand, we can see that the total energy of a photoelectron, when excited by a light quantum, at the surface of the anode is the following. Here, phi is the energy needed to extract an electron from the anode surface, also called the work function. And it is a property of the material used on the anode. Then, the maximum kinetic energy of a photoelectron is the following. At this point is where Einstein used the Planck's discovery, meaning that the energy is simply the product of the Planck's constant times the frequency of the light quantum. This is in principle the most important part of Einstein's interpretation of the photoelectric effect, as he proposes that light is composed of discrete wave particles. In other terms, light is nothing else than energy delivered in tiny packages, that, as commented before, Einstein called the light quanta. If we use this definition energy, then we can see that the maximum kinetic energy of a photoelectron is written as follows. Also, if we suppose that the kinetic energy is zero, meaning the photoelectrons do not move, then we have the following. From the last equation, we can calculate the minimum frequency at which the photoelectrons can be extracted from the surface of the anode. Finally, note one more time how the photoelectric effect only depends on the energy of the light quantum and the work function of the material. The intensity is not important for the effect to appear. Up to this point, we have used the term light quantum, referring to the particle of light. Actually, this was the original term used by Einstein. But nowadays we use the term proposed by Gilbert Lewis. This is the photon. The final characteristic of the photoelectric effect we have to discuss is the immediate emission of photoelectrons when the light source is on. It is generated by the so-called one-to-one interaction, meaning that a single photon interacts only with a single electron. It is clear that this is only possible if the photon behaves as a particle, rather than a wave. Finally, because of this discovery, Albert Einstein was awarded with the Nobel Prize in 1921. In addition to the photoelectric effect explanation, Einstein proposed the relativity theory, and was responsible for a convincing model of the Brownian motion, proving the existence of atoms and molecules. All these three discoveries were published in 1905, also known as the Annus Mirabilis papers. Let's solve an example to see how the photoelectric effect works and to predict the cutoff frequency. Example 10. Calculate the minimum frequency to extract photoelectrons from an anode made of gold, and explain the physical meaning of the result. Could you solve it? Answer. We know that the cutoff frequency is related to the work function by the following equation. The work function of golf is about 5.2 electron volts. Also, note that we need to express the Planck's constant in terms of electronvolts. Then, the cutoff frequency can be calculated by replacing the values in the equation above as follows. Finally, the cutoff frequency for a gold anode is. This frequency is equivalent to a wavelength of about 240 nanometers, meaning that in order to extract photoelectrons, it is needed ultraviolet light. In the next video, we will discuss the concept of photon, its characteristics, and the implications for the modern physics revolution. Stay tuned.